Hi all, good morning everyone. I'm presenting the paper A System Architecture for Running Big Data Workflows in the Cloud, written by Andrew Cashlew and Xiong Lu, Department of Computer Science from Wayne State University. The paper flows first with the introduction, then the challenges faced by the scientists while running big data workflows in the cloud, such as a resource such as platform heterogeneity challenge, resource selection challenge, environmental setup, and all those things. Later they goes on with the implementation. So before to that they have the data view of all the workflows, then they have the implementation in the case study. But before going for the explanation of the paper, let's study some key points to understand the complete architecture of the big data workflows. First, it would be big data. What is big data? And then what is cloud computing and what is workflows? So let's start with what is big data. Big data is extremely large data sets that may be analyzed computationally to reveal patterns, trends, and association, especially related to human behavior and interactions. So daily we use the data, and that's a normal data. And how it is related to big data? Let's take the example of some company. Any company employees, when they are searching any websites, those data will be saved in the cookies. So all those data saved at the end is just called an information or a data. So how it will be turned to the big data? So what does company do? Just to know how many times employees have used the site, like example, let's say the YouTube, how many times the YouTube site is browsed. So all those analytics will be done. So based on that data, after analytics, all the data will be saved as site. So that is called a big data. So that's a difference. So let's see what is cloud computing. It is the practice of using a network of remote servers hosted on the internet to store, manage, and process data rather than the local server or a personal computer. A cloud computing system keeps its critical data on internet servers rather than distributing copies of data files to individuals' client devices. Example like a video sharing. Cloud services like Netflix, for example, stream data across the internet to player application on the view device rather than sending customers DVD or a Blu-ray physical disc. We'll see how Netflix uses big data analytics for its business success. First, Netflix was nowhere. So when it launched in 2016, they were just selling the primary DVD or mailing business. Then they launched the Netflix prize, offering $1 to the group which could come with the best algorithm for predicting how its customer would rate a movie based on their previous ratings. So first they used this big data analytics, that is, they started analyzing, like analysts were limited by the lack of information they had on their customers because only 4 data points, that is customer ID, movie ID, rating, and the date that the movie was watched, were available for analysis. So as soon as the streaming became the primary delivery method, many new data points on their customers became accessible. Data such as time of a day that movies are watched, time spent selecting movies, and how often playback was stopped, all became measurable. Effects that this had on viewers' enjoyment could be observed, and models built to predict the perfect storm situation of customers consistently being served with movies they will enjoy. So that is how they have analyzed. So based on the how many times the viewer has watched the movie, so based on that, the same kind of movies they started uploading or sharing with them. So that is how the Netflix grew. So next, see what are the workflows. So, unlike workflows run in traditional on-premise environments such as standalone workstations or grids, cloud workflow relies on dynamically provisioned computing, storage, and network resources that are terminated when no longer needed. This dynamic and volatile nature of cloud resources, as well as other cloud-specific factors, introduce a new set of challenges for cloud-enabled. But before going to the paper, let me understand one more point: what are workflows and how it will be implemented with the big data. So to understand that, let's take the example of drawing the blood. Drawing the blood is a necessary task required to complete the overall diagnostic processes. If something happens and blood has not been drawn or the data from the blood test has been lost, it will be direct impact on the veracity or the truthfulness of the overall activity. What happens when you introduce a workflow that depends on a big data source? Although you might be able to use existing workflows, you cannot assume that a process or workflow will work correctly by you just substituting a big data source for standard source. This may not work because standard data processing methods do not have the processing approaches to perform the handle complexity of the big data. So what they do? First, identifying the big data source you need to use, map the big data types to your workflow's data types, then ensure that you have the processing speed and the storage access to support your workflow. Then select the data source best situated to the data types. Then modify the existing data workflow to accommodate big data or create a new big data workflow. So that is how it is. So let's see what are scientific workflow management systems. Cloud workflows rely on dynamically provisioned computing, storage, and network resources that are terminated when no longer needed. So this dynamic and volatile nature of cloud resource, as well as other cloud-specific factors, introduce a new sets of challenges for the cloud-enabled, so-called scientific workflows management systems. Ad hoc implementation account for particularities of their data of the target application. They do not address the breadth of challenges in managing scientific workflows in the cloud. Thus, more generic implementation independence so is needed that would address a broader scope of cloud-related challenges in a systematic way. But here, scientific workflows can be thought of as data pipelines consisting of heterogeneous software components connected to one another and to some input data products. These components may include local executable programs, scripts, web services, such as HP jobs. Such workflows are designed using scientific workflows management systems. Scientific workflow management system will help remove technical burdens from researchers, allowing them to focus on solving their domain-specific problems. So let's see what are the challenges they face when they are running on the cloud. But here, before going for the challenges, let's see what the paper has presented. First, they have identified the key challenges of running big data workflows in the cloud, and then they have proposed a generic implementation independent system architecture that addresses those challenges, and then they have developed a cloud enabled system, the scientific workflow management system called DataView, that delivers a specific implementation of architecture and present a case study from the automotive industry domain to validate our solutions. So we'll see the challenges. In this work, they have run the entire system in the cloud according to the all and the cloud approach. The system is deployed in a virtual machine in the cloud and is accessed remotely through a web-based GUI interface. Scientific workflows management system schedules workflow to run on multiple virtual machines such that different parts of workflows run on different nodes. So let's see the challenges. The first challenge would be platform heterogeneity challenge. like when there are different types of clouds, so using those different types of cloud and enabling it in your workflow, it will be a difficult. So we'll see what kind of difficulty they face. First, it is connecting to the cloud. The process of connecting to a cloud, to a particular cloud, is defined by the cloud provider and is generally different from different vendors. Connecting cloud typically involves providing a security key, and in some cases it depends on the configuration, and loading the client software in the case of like both Eucalyptus and OpenStack clouds. Next comes to resource provisioning. What happens in this? The interface exposed by various providers to provision cloud resource are also different. There exists no standard for provisioning resource in different clouds in a uniform way. While Amazon EC2 provides Java API tools to manage its cloud resources programmatically, whereas OpenStack provides RESTful interface as well as the Python and command line implementation of OpenStack. So while coming to the creating machine images, here the Eucalyptus cloud uses the image of the output and it will be saved within the file system of that instance. Because it uses local drive of the virtual machine, it requires large amount of free disk by the snapshot. But whereas OpenStack, it uses the Nova image create command is run to save images files outside the virtual machine, whereas Eucalyptus uses the save the image inside the virtual machine, whereas OpenStack saves the image outside the virtual machine. So that is how the conflict becomes. Here it comes the challenge of creating a machine images. Next, a big challenge will be migrating workflow between cloud platforms. How does it? Cloud providers support different sets of instance types. Example, Amazon EC2 Cloud have 27 instance types while OpenStack offers only 6 types. So while migrating the data from one cloud to another, the instance types number will be different. So it will be difficult for them also to adjust the data whatever it is migrating from one cloud to the another. So that is how the difference comes here. The next we'll see the resource selection challenge. Here I feel the resource selection challenge will be the great problem. How it will be? Running a workflow in the cloud always involves a choice of number and types of virtual machines to execute the workflow. We'll see what kind of virtual machines they select and depending on what in the next slide. Here, given a particular configuration such as whatever it might be, a 4M1X large or 7M3X large and 3 C1 medium servers, it is hard to determine an optimal schedule and hence an optimal running time. Since the scheduling problem is NP complete in general, let's see the example. We'll take the same example of the clouds Amazon EC2 and the OpenStack. The Amazon EC2 has 27 instances. If you're taking the virtual machines, 3 virtual machines, so it will be like 27 to the power of 3, so the total will be 19,1683 or somewhat. So there are so many possible choices to select which resource they have to. And this number will go exponentially if the user would like to employ more virtual machines. So that is how the difficulty comes. Next goes resource volatility challenge. Cloud computing allows to provision and terminate virtual servers and storage volumes on demand. However, due to various failures, loss of resource often occurs. Such dynamic nature of cloud resource has several important implications on scientific workflow. We'll explain what it is by the following. The persisting output data products. As the workflow execution occurs in the cloud, the output data products that are of interest to the users are also initially saved in the cloud. After execution is complete, user may often need to terminate the instance on which it was running. To avoid paying for the unused virtual servers, thus the scientific workflow management system should provide a way to persist output data products to avoid their loss. The next comes registering the new components or the data products. When the cloud has only one component to share the data, when you want to share the lot of data by different people, then it will be difficult. Next, coming to cataloging virtual resources. Running workflow in the cloud involves executing individual components residing in the different virtual machines, which require connection related details for each virtual machine, such as its IP address, credentials, and status information. It is challenged to capture in a timely manner changes in virtual machine configurations. Next, coming to environmental setup. Scientific workflows are often built from components required certain libraries and packages to run, so it will be difficult for them to set up the environment. Next, coming to distributed computing challenge. The fact that workflow execution is performed in a distribution manner complicates big data workflow management system in several ways, such as passing big data products to consumer components, logging and workflow monitoring, and preventing the collections. Next will go a system architecture. We'll view the data workflow. Here there are a lot of points such as the main subsystem, data view, our workflow design and configuration. We'll see what is the design and work configuration. The workflow design and configuration subsystem provides GUI for the users to design workflows as well as to specify workflow configuration. It consists of two major components. Design component provides a web-based GUI, allowing users to compose and edit save workflows. Workflows are edited in the browser's window by dragging and dropping components and input data products onto the design panel and connecting them to the workflow. Next, see what is workflow engine. Workflow engine is a central system enabling workflow execution. The translator module is responsible for producing executable representation of workflows with the specification written in a XML-based SWL language. We'll see what is workflow monitoring. I'm just giving you the definition of those. We'll see how it works in the next slide. The workflow monitoring subsystem keeps track of the status of individual components such as initialize, executing, finished, error. So data product management. The data product management subsystem stores all data products used in the workflows. Initially, all data products reside on the master node. We'll see this is called a data view. So here is a presentation layer, the workflow management layer, task management layer, and infrastructure management layer. The presentation layer contains the client side of the part of the system. The workflow management layer contains subsystem orchestrating the work progress of the data flow, and the task management layer contains the modules that ensure successful execution of individual tasks in the cloud. Finally, the infrastructure layer contains the underlying IaaS cloud platforms, whereas workflows are dispatched according to the all in the cloud system runs in the master node. So let's see what is provisions. I have explained you what is presentation and visualization before, and the workflow design and configuration is also done. Here the workflow monitoring, which monitors all of the data over here. So next, see what is provenance data management. It is a subsystem responsible for storing, browsing, and querying workflow provenances. What is task management? It enables executing heterogeneous automatic tasks such as web services and scripts. So we'll see what this cloud resource management does. It is a subsystem plays a key role in provisioning data, cataloging, configuring, and terminating virtual resource in the cloud. Its architecture is here. Here it subsystem consists of 7 modules. That is VM provisioning module. It is responsible for creating virtual machines and creating virtual machines from images saved beforehand. These images include the data view kernel needed here to run the workflows, whereas machine image management, a catalog of machine images and metadata for each image. These metadata along with all other metadata about available virtual resources are stored in virtual resource catalog, which addresses the C3 challenges. Next comes EBS volume and the S3 provisioning. All this data will be managed. So let's see what is the implementations and how they have done it. They have done a case study. We'll see. They have implemented the proposed data view architecture as a web-based application written in Java. To test implementation and validate the data proposed architecture, they have conducted a case study by developing a data view in Amazon EC2 cloud, as well as the Future Grid Eucalyptus and OpenStack, and running a big data workflow from the automotive domain. As a result, we're similar in different from clouds due to space limit here. Our data, what they have done, they have taken the 50 drivers and the data of 1 hour worth. What is it? How often does the driver accelerate and then suddenly brakes? And how smoothly does the driver accelerate? And one more, how gradually does the driver brake before making a turn? The workflow first extracts the data related to the acceleration and braking speed up and braking before turns using extra speed up, extra braking turn components. It then analyzes each of these factors and derives a number of characterizing each of these aspects. Here, then if the more number of times the driver has used the brake or accelerated, then he would fail. This is how they have just taken the four people example and they have given their percentage over here. So if the number is more, then he would be failed. Here the Janice Henderson number is 5.5 for the abrupt acceleration and braking, so that is how he has failed. The next, see the analysis. This is what they have done, the analysis, running a big data workflow in the cloud using different number of slave nodes. And here, before using, if they are while migrating the data flow from one cloud to another, it is like we have big data movement technique that supplies large files to target virtual machines by attaching EBS volume containing required files to the virtual machines that consume these files. To test the technique, they have measured the time to transfer 3 GB data set from one virtual machine to the another when using traditional file transfer protocol when using a proposed technique. The result is this. So as the obtained result confirmed, the proposed technique allows user to transfer big data files like the reasonable rates even when network performance limited. Next, we assume that EBS volume used to supply data to the target machine exists in the same region as the same machine itself, since the region of the volume is specified explicitly at volume creation time and thus in the control. This assumption is easy to meet. When they have used the EBS volume, it has taken less time, so you can see the difference over here. What is the difference? And when they're using the slave node while transferring the data, just a normal nodes, the time taken by them before using any slave nodes is normal. It's something 8000. This is in a dark thing. And when they're using some slave nodes, the time is less. This is how the analyzation is done. So let's come to the conclusion. What is the conclusion of this paper? First, they've identified the 4 key challenges running big data workflows in the cloud. Second, they have proposed a generic implementation, independent system architecture that provides the guidance for different implementations of big data oriented scientific workflows management system in the cloud. and addresses most of the challenges discussed. Third, they have implemented the data view of the system that delivered specific implementation of architecture and ran a data workflow in the Amazon EC2. Then they have used the data of 50 drivers and the future grid eucalyptus and future grid OpenStack clouds to validate that the system architecture is platform independent. Like they can transfer the data from one cloud to the another, else by using some slave nodes or by using EBM volume. So let's see what are the future works. They have planned to explore the workflow scheduling techniques in the cloud that take advantage of workflow profiling and runtime behavior analytics module. So they also will create the more large-scale big data workflow from the automotive domain as well as workflows from the bioinformatics and physics. So well, I have presented the document. So let's overall about this. I feel, according to my view, the main big challenge of the data workflow is resource selection. Why? Because when there are different kinds of instance, like let's take the example of Amazon EC2, it has a 27 instance. When they're using 27 instance and different kinds of virtual machines, when they are needed, then it will be difficult for them to select which flow they have to go, which resource they have to select and which flow have to do. That is all my view, friends. Thanks for watching the video. Have a good day. Bye.